Let's consider the sums and products of rational and irrational numbers. We are given 6 expressions, and we're told to classify each expression as rational or irrational. We'll start with the one that says 9 pi. We know that pi is an irrational number, 3.14159, and the decimal part of that number goes on forever with no pattern. So 9 times pi would also have a decimal portion of the number that goes on forever with no pattern, so it's irrational. The next example, 5 root 3, that is an irrational factor, times 2 square root of 3, another irrational number. 5 times 2 is 10, and root 3 times root 3 is square root of 9 or 3. So expression B would actually simplify to 10 times 3 or 30. That's a rational number. Example C, 6 times the square root of 9, that's 6 times 3 or 18. 5 root 16 is 5 times 4 or 20. 18 plus 20 is a rational number. The next example, the cube root of negative 27, that is negative 3, which is a rational number. But the square root of 6 is an irrational number. So when I subtract off an irrational number, my answer is going to have a decimal part again, which has infinitely many digits and has no pattern. That expression is irrational. The square root of 7 is an irrational number. The square root of 28 can be rewritten as the square root of 4 times 7. I could simplify this whole expression to 1 root 7 plus 2 root 7, or 3 square root of 7. That is still an irrational number. The last example, 5/11ths, is a fraction. 4.875 is a rational number because it's a terminating decimal. So we know we could write that also as a fraction. And the sum of any two fractions can be written as a fraction. So this one is rational. Look at another example here. Classifying each expression as rational or irrational. Let's kind of be creative when we consider these. Is there any math that we can do? Knowing the square root of A times the square root of B is the square root of AB. This first example is the square root of 625, which is 25. That's a rational number. How about the next example? Let's write it as a single fraction, the square root of this fraction. 63 divided by 7 is 9, and the square root of 9 is 3. This is a rational number. So oddly enough, in the first two examples, in the first example, while each factor was irrational, the product was rational. In the second example, each part of the fraction was irrational, but when I simplified it, it was rational. Now the next example, we know pi, again, is an irrational number, 3.14159, infinitely many digits. If I add to that expression 5 6/10, the only part of really pi that changes, right, is the ones place and the tenths place. So this is an irrational number. It will go on forever with no pattern. Now the next example, we follow order of operations and we multiply before we subtract. And any number minus itself is 0. So the irrational number 12 pi minus itself is rational. Now sometimes you're asked to subtract expressions which are in the form of square roots. To do this, we want to rewrite 11 square root of 8. You know the square root of 8 can be rewritten as square root of 4 times 2, where 4 is a perfect square that we can take out of the radical when we take the square root of it. So we can rewrite this expression as 11 times 2, square root of 2, or 22 root 2. So let's take a look at the original expression, rewrite the 11 square root of 8 this way. And now we can think of these two irrational numbers kind of like like terms. We can subtract them and write a single radical. So we have subtracted the expression, and the answer is 19 square root of 2. Next example. Which expression, when evaluated, is irrational? So let's take a look, and we will try to be, again, creative when we consider these. If we have a fraction where the numerator and the denominator are both square root, we can write it as a single fraction under the radical. Now 2/8 simplifies to 1/4. I can take the square root of 1 and the square root of 4, so the square root of 1/4 is 1/2. That is not an irrational number. Let's look at example option B. Let's write it as a single fraction under the radical, 8 divided by 2 being 4, square root of 4 is 2, again, not irrational. Next one is a really interesting example. We can have that square outside of the parentheses or inside the radical, and the square root of 64 is 8, which is a rational number, so the answer is not C. For D, what would you do to simplify this one? Let's have a single radical and have 2 times 8 underneath the radical. You know the square root of 16 is 4. So that is not irrational, which tells me option E must be my answer. Let's take a closer look at it. I have rewritten 8 as 4 times 2. I can take the square root of 4 out of the radical. So we're left with, that should say, 1 square root of 2 plus 2 square root of 2 is 3 square root of 2. The answer is E. A couple more examples. Which expression simplifies to this that's given? It cannot be A, because 10 is not a perfect square. Neither does it have a factor which is a perfect square, so it cannot be simplified. For that reason, it can't be B. However, 20 can be rewritten. So let's check out option C. 20 can be written as 4 times 5. X cubed can be written as x squared times x. Now let's take the square root of the perfect squares. We'll take the square root of 4 out of the radical. We'll take the square root of x squared out of the radical. And we're left with 2x. What's left in the radical is square root of 5xy. That is not the answer. It must be option D. We can prove it right here. We're going to rewrite each of these factors as a perfect square times something else. Let's take the square root of 4 out of the radical, the square root of x to the 4th, and the square root of y squared. What comes out of the radical is 2x squared y. What's left in the radical is 5x. That's my answer. And our very last example, Cheryl claims that any irrational number, when you square it, will result in a rational number. So Cheryl has made a few observations, and this is her claim. To disprove her claim, all we need to show is one counterexample, but let's try to take a look at what she's saying. And let's look at the second example in, and let's square this one and see what happens. Well, when I square the numerator, I get 3. When I square the denominator, I get 2. 3/2 is a rational number. Cheryl might be onto something. Let's take a look 2 more examples over at the square root of 2. Let's square it. The square root of 2, when you square it, is the square root of 4, which is 2, also a rational number. Let's look at that last example, 5 root 3. Let's square it. So you're going to square each piece. We're going to square 5 and then square root 3. So that's 25 times 3, or 75. That's a rational number. So at first you might be inclined to think Cheryl is correct. Let's take a look at pi now. Pi is an irrational number. Let's square it. You'd get pi squared. Pi squared is still an irrational number. It's not like the square root of 3 squared, because square root and squaring undo each other. Pi is not an operation. We do not have inverse operations going here. That is an irrational number. I have hereby disproven Cheryl's claim. But we can also take a look at the cube root of 2 and square it and see what happens. Let's put that 2 underneath the radical. Now let's square 2. And so we're looking at the cube root of 4. Is 4 a perfect cube? It is not. So therefore, this is an irrational number. Here's another example that disproves Cheryl's claim. In the first example, we can square the numerator and square the denominator. When I square the numerator, I just did that, it's the cube root of 4. When I square the denominator, it's 3. That numerator is definitely an irrational number, so the fraction itself is irrational, and Cheryl's claim is false.